Okay, we are live now.
Great. Shall we start the recording as well?
Yes.
So in the meantime, welcome. I will start with the opening. So welcome everyone that allocated some time to join us today. My name is Elizabeth Neranzis from Alpha Consult, Exploitation Manager of the ENCASE project. It is a pleasure to open this session, which represents a joint initiative of 4 EU-funded projects: ENCASE, CorEU, EasternLights, and HERCCULES. The context is clear. The increasing complexity of energy transition scenarios in Europe and worldwide require closer collaboration between research, policy, and practice to ensure that cutting-edge technologies and effective future-ready solutions are in place to tackle the climate crisis. Building on this, a cluster of EU-funded projects, ENCASE, CorEU, EasternLights, and HERCCULES, in the field of CCS and CCUS, are joining forces in a dedicated online session, which is this one, to foster cross-project exchanges, raise awareness of ongoing developments in the field of energy transition, and increase the visibility of policy recommendations. Beyond the showcasing of individual results, you will have a joint discussion in order to ensure that the project's messages reach a wider community. And today's session reflects that ambition. So rather than presenting results in silos, we are creating a shared platform to examine CO2 impurities from multiple perspectives: technical, regulatory, systemic, and market-oriented, across the full chain of the CCUS value chain. Before starting, we have some few housekeeping rules. Massimo, if you can please showcase the slide. This applies to all of us, including the speakers. So, as mentioned, we are live on YouTube. The meeting is being recorded. So we will keep everybody's audio and video disabled during the presentation to ensure the best audio quality for everyone. Only reactivated them for specific intervention and where requested. Time management, especially for speakers. If the intervention and discussions are being a bit too long, you will see a rabbit appearing. This means that we need to wrap it up, and this is a signal for you. For what concerns question and answers, the chat is deemed for this purpose. Please stay on topic, and we will gather and collect the questions and have them replied to you. For what concerns contact and networking, if you need any contact of the participants, please send an email to Massimo at ms@alphacons.eu, because we do have to comply with GDPR regulations. So I think that's it for my side. Before concluding this opening, I would like to thank all partners from the ENCASE, CorEU, EasternLights, and HERCCULES projects for their collaboration in co-organizing these joint initiatives. And now, without any further ado, I would like to introduce ENCASE's project coordinator, Lan Liu, for the welcome and objective sessions. Lan, the floor is yours.
Yes, thank you. I'm sharing my screen.
I'm sorry, Lan, just before starting, a couple of things. Please turn off your audio. Okay.
That's done, yeah.
Okay.
Yeah,
if you're not a speaker, please turn off your audio and your camera and microphone, and turn them on only if you want to speak. You can use the chat for eventual questions here on YouTube. We'll check both. And please, if you ask a question, mention also the person or the project you're referring to, We will try to answer to all the questions, but also we will try to respect all the timing to give the right space to everyone involved. Just a reminder for clearness, the workshop is live on YouTube and will be recorded, and the recording promoted on ENCASE communication channels like LinkedIn, X, and so on. I'm sharing here in the chat all the links to ENCASE social media channels. If any of your colleagues or contacts are unable to connect via WebEx, they can follow the webinar as said live on YouTube. You can find the link in the chat. I'm sorry to interrupt you, Lan, but we can start.
Yeah, thank you. Thank you. I'm Lan Liu from Institute for Energy Technology Norway. I'm a technical coordinator of ENCASE. I would like to welcome everyone to join this webinar, which is organized by ENCASE. Today, we'll talk about the impact of CO2 impurity on the CCUS chain from different perspectives. So we will take this opportunity to share our knowledge, to exchange our experience, and raise awareness of ongoing development in CCS. As we all know, none of our CO2 streams is truly pure. I'm an experimentalist. When we start doing experiments with CO2, and one question we should ask us before doing the experiment, what grade of CO2 we should use to our research, to our experiment. So when a CCS infrastructure being designed, built up, operate, the same question should be answered. What the CO2 purity one should reach to meet all the necessary requirements, but not make the project too expensive to implement. So there are several CO2 purity recommendations. They depend on the type and design of the transport and where to store and where to use. There is no universal purity recommendation. Technically, there are few barriers to achieve high purity of CO2. One can get almost 100% purity, but it requires additional cost and energy consumption. So that means we need to balance between the safe and the reliable operation of CCS system and the cost, legal, and environmental aspects. So the type and concentration of impurity depends on the capture sources and the capture technology. So the impurity can be divided into different groups, like non-condensable gases, for example, nitrogen, argon, hydrogen. Some impurities are reactive. For example, water, NOx, SOx, H2S, and CCS CO2 streams can also contain hydrocarbons, metals, and particles. So the most important impact of impurity is that impurity changes the phase behavior and the thermophysical properties like density, viscosity, compressibility, and speed of sound, for example. So impurity shift the phase boundary, widened phase envelope, and for most impurity to higher pressure. This leads to a narrower operation windows. Impurity also adds uncertainty to phase behavior. This needs us to set actual safety margin to take account of the impact of those impurities. Impurity also affect the measurement accuracy, monitoring interoperability, and verification credibility. Another aspect is unsafe operation of CCS infrastructures. Impurity can affect integrity of infrastructure, both transport and storage. For example, material degradation, the impurity can drop out because the solubility varies with temperature and pressure, and one impurity can affect another impurity's solubility, so it makes the situation complex. For example, if water drop out to form free water and react with some reactive impurities to form acid, then people can risk to have corrosion to the pipes, to the vessel walls, and also can risk to have mineral dissolution in well and reservoir. Another hazard is solid blockage. The solid particle can come from chemical reaction, precipitation of salts and scale. When the temperature and pressure in the hydrate formation zone, hydrate particle may also form. Some solid particles just come from the capture site. So those solids can clog to reduce the injectivity of well and near well region, and then reduce the capacity of the reservoir. If those solid particles block the venting valve, people can have a risk on the hazard of unsafe operation of pipeline, for example. Another phenomena is phase transition. So the temperature and the pressure varies along the whole chain, especially in well. The temperature and pressure can change rapidly. So when this happens, you may have multi-phase flow, and multi-phase flow can introduce other flow assurance issues like vibration, like flow and pressure instability. Those the operator of the infrastructure doesn't want to see. So to tackle all those challenges, we need close collaboration between the different projects working on CCS. And today we have 4 different EU projects: ENCASE, CorEU, HERCCULES, EasternLights, to join this webinar. And I see this as a very good starting point for such collaboration, because all these 4 projects working on different area, different parts of CCS chain. So again, welcome to this webinar. I hope you get inspired by today's webinar. And as the technical coordinator of ENCASE, I would also like to say a few words about ENCASE. So ENCASE is a European network of research infrastructure for CO2 transport and injection. So to tackle the challenges I already mentioned above, like phase behavior, accurate measurement, flow assurance issue, ENCASE also covered a specific area, which is also a challenge. It's lacking of facility to test and verify instrument and equipment under relevant condition of CCS. So ENCASE will improve research infrastructure, train the staff, and serve the future industry needs. We will co-develop the instrument and equipment with our industrial partners. We will provide high-quality data to develop, improve the software and tools. We also develop digital technology and tools for optimization of research infrastructure operation, train the future workforce, and we established new social innovation labs to integrate research infrastructure to society. So this is from me for this very brief introduction of ENCASE. I think I should give the floor to other projects to present themselves. Yeah, thank you.
Thank you, Lan, for this introduction. So without any further ado, I would call up the next speaker. So please, I think we have CorEU, so the coordinator of CorEU is, if I'm not mistaken.
Yeah, I think the coordinator is here. Francesco, are you here? Looks like he's not, so maybe
Okay.
I can do a quick introduction on the project, but I didn't prepare any slides. So on behalf of CorEU, we are one of the largest carbon capture and storage projects funded under Horizon Europe. And the project is running since January 2024. And we are a very big consortium with 43 partners from 13 different countries. And we're building a CCS network connecting emitters with storage sites. And in the project, we are developing 4 different transport and storage routes in Poland, in Czech Republic, Ukraine, and in Greece. And the flagship demonstration is the Prinos plant in Kavala in Greece. And impurities are very important in our project because later in the developed routes, the CO2 will come from different sources because we're establishing hub concepts. And our partners investigate how the impurities affect the safety and the performance and also the cost of the CO2 transport and storage. They're doing a lot of experimental work, thermodynamic modeling, and also simulations. And I think they will explain later what they are doing in particular.
Thank you, Katrin. I would call the representative for HERCCULES at this moment. So, okay, network issue. Okay. Okay, so I think it will be Maurizio, if I'm not mistaken. Maurizio, the floor is yours.
Yes. Can you see my screen?
Yes.
Yes.
Okay. Thank you for the introduction. I'm Maurizio Spinelli from LEAP. I'm the coordinator of the HERCCULES project. So HERCCULES, in 1 minute, HERCCULES is a very large innovation action focused on the demonstration of the entire CCUS value chain in Southern Europe. The project in particular aims to test several carbon capture and CO2 utilization technologies for the decarbonization of cement and waste-to-energy sectors within 2 industrial clusters located in Italy and in Greece. So within the project, we are building and demonstrating 3 different CO2 capture systems, as well as 3 CO2 utilization and waste material recovery processes for the production of low carbon concrete. And at the same time, we are exploiting 2 storage sites located in Southern Europe, in particular Ravenna in Italy and Prinos in Greece, in order to characterize and close the full demonstration of the CCUS value chain. Then, of course, building on all the experimental results, we will also provide several full-scale case studies. And then HERCCULES is much more than this. We have a lot of activities in several areas. I have no time to talk about all these activities now, but I'm just pleased to show the map on the right of our consortium, which has grown since the project. I know that many partners of ours are joining this webinar today, and some of them will also contribute with some presentations. Now, going to impurities, regarding impurities, as you can imagine, given the scope of the project, their management is a key aspect across many of our project activities. So first of all our carbon capture systems are designed to achieve high, of course, very high carbon capture rates, but also at the same time, very, very high CO2 purities in order to meet the specifications required for transport, utilization, and storage. And in some cases, also even exceeding those specifications to reach the food grade purity standard, which is something that we have already demonstrated in one of our pilots. Then most of our technologies are integrated with a dedicated cryogenic purification unit for the removal of non-condensable gases, and together with also auxiliary systems for the deep removal of other contaminants like NOx, SOx, dust, and so on. In one of the pilots, we are currently struggling and working to implement the equipment needed to achieve such strict limits for these contaminants. Finally, just a point, in one of our carbon capture pilot plant, the calcium looping one, we will also test the capability of the sorbent, the calcium-based sorbent, to co-remove some other impurities, such as acid gases and sulfur compounds. So that's all from my side for the moment. Thank you very much for your attention, and I'm very much looking forward to the discussion. Thank you.
Thank you, Maurizio. So I would call the representative from EasternLights, please. If you can please start sharing your screen.
Yeah, just I see in the chat that Francesco is requesting, if possible, to present now.
Absolutely, absolutely.
Yeah,
If you hear, do you hear me? Do you hear me well?
Yes, loud and clear. Yes.
Okay, thank you very much. Apologies for before. I had to restart. So I share the screen. Is it okay?
Yes.
A couple
Yes,
of slides.
yes, absolutely.
Oh, thank you very much. Please tell me if you see the screen. Do you see it?
We see all your screens.
Perfect.
Perfect.
Now we have only one, right?
Yeah.
Okay. So thank you for joining the webinar, and welcome CorEU. It's called CO2 Routes Across Europe. It's coordinated by Sintef Energy Research. I represent the Sintef Energy as a coordinator, but the coordinator is actually Chiara Caccamo, who is not here today. Key fact for key points is the project started in January 2024 to December 2027. So it's a 4-year project. Co-funded by the European Commission, about 35 million euros. So it's a fairly large project, and we do research on many, many topics, including CO2 purity. We'll get back to that later on. We have 43 partners that include the emitters, technology providers, transport system operators, and different companies that represent technology in the field. And the key part of the project is demonstrating key technology across the chain. So we're demonstrating from capture to storage in Greece. We actually have a bit broader scope than that, but the key demonstration will happen in Greece in a site which is called Prinos, where we're gonna inject some CO2 that we capture in an Edison plant still in Greece. So basically the CO2 capture will be captured by a project which is called High Record, and then transported through some pressurized vessels that will be developed in CorEU or are being developed in CorEU, down to a site in offshore Prinos. In addition to that, we have several routes, which include Central East Europe, where M&D is working on onshore storage, or at least they're trying to make it possible in the Czech Republic. And Poland, we are also looking at the Poland route with offshore reservoir exploitation out in the Baltic Sea. In Ukraine, also, we are looking at both onshore, mostly onshore, I would say, storage because of obvious reasons, I'd say. And we're also looking at some routes that could include some parts of Czech Republic and the connection between Poland and Ukraine. In addition to that, we are working on LCA, environmental impact and risk, and several scenarios for cross-border CO2 transport and infrastructures. So this, in short, you will get back with our technical people on the purity criteria. I think we will have a lot of discussion on that. But thank you, everybody, and apologies for the issues with the internet now solved. So that was it from my side.
Thank you, Francesco. No problem. Connection issues happen, so just chill. So now, without any further ado, I would call the representative from EasternLights to showcase.
Just 1 second. Do you see my screen?
Yes, yes.
Perfect. Well, hello, everyone. First, I would like to thank you for organizing this webinar. I think it's a great opportunity to work together in the field of CCUS. It's a pleasure to be here. My name is Veronika Georgieva, and I am project manager at HOST Bulgaria, the coordinator of the EasternLights project. EasternLights is a pilot demonstration project implemented by 19 partners from 8 different countries, and is focused on the transportation of CO2, its injection, and permanent storage underground in northwest Bulgaria. This is a 4-year project which started in September 2024. About impurities, they're not a central technical parameter for the EasternLights project. However, they're considered in both storage and transport because they strongly affect safety, design, and cost across the entire CCUS value chain. It was already presented by the technical coordinator of ENCASE, the impact and the importance of CO2 impurities, but I will try to be just very quick on this. And I would say that the trace impurities in captured CO2 can create a domino effect. Toxic components increase hazard zones, while non-condensables affect decompression behavior. And it was already mentioned, may require stronger pipelines still to prevent running ductile fractures. They can also shift the CO2 phase envelope, increasing the risk of two-phase flow and freezing. In addition, trace water with SOx, NOx can form corrosive acids. So as a conclusion, I would say that projects must balance the cost of CO2 purification at the source with the much higher cost of building infrastructure that can actually tolerate unstable and corrosive streams. Thank you. I'm trying to
very Thank you very much, Veronika.
You're welcome.
For your presentation and for being short as planned. So now ready to dive into session 1 regarding the technical and safety impacts impurities. So for this first session related to impurities in captured CO2, small but relevant to the success of CCS, I'm pleased to call Manuele Gatti and Roland Spahn, respectively from Politecnico and from CorEU. I think Manuele Gatti, you will start first. Please, the floor is yours.
Yeah, thank you. Thank you. Good morning, everyone. I will start with this presentation and then leave the floor to Professor Spahn. When talking about impurities in CO2 capture stream, as introduced previously, the list can be very long. So the idea here is not to provide examples of composition of specific CO2 streams, but rather talking about categories in this very first part. The factor affecting the presence and the amount of impurities are several even within the same sector, even within the same plant, because it may depend on if we are looking at the industrial process, even on the raw material characteristics, if we are looking at flue gases, on the fuel, on combustion conditions, but then considering that before transport and storage, you have the capture step, even the interaction between the materials of the capture technology and the stream bearing the CO2 may have a role in producing contaminants or species that come from degradation products. So here is just a list of different type of streams. For instance, we know that in combustion flow gases, the major component are the one from combustion. So aside from CO2 and water, we have also the excess air components. But then the impurities can be quite a long list depending on the fuel and the combustion conditions. So not only NOx, SOx, and CO, but if we deal with some solid fuels, especially when they are heterogeneous, like from biomass, waste to energy, or even coal, the list becomes very long and includes even other species. When looking for industrial processes, we know that the raw material plays a role, but also the type of process generating the CO2. So for instance, in the field of cement, we know that the concentration of CO2 is one of the highest, but then aside from that, we can also have species like VOC, dust, of course, coming from the process, NOx, OX, and so on. If we look for the steel industry, the variability is even larger because there are multiple sources of CO2 in a steel making facility, and we can add to the typical list even for certain steel making routes hydrogen and even sulfuric species and metals. Then when talking about the capture route, of course, here are the three typical capture route. If we talk about post-combustion with solvents, we know that the capture stream coming out of the stripper can be at very high purity, but again, the impurities are the key point and need to be monitored and, if needed, controlled in their presence in the CO2 capture stream. From oxy-fuel is not so different than from combustion with air, but in reality, the difference is in the composition of the different species, because we take out the nitrogen, and therefore some species can be much, much higher concentrated, not only the CO2. Finally, for pre-combustion, we have that the origin of the syngas mostly sets the type of compounds that are included. Of course, then the capture technology, like for the other routes, play a role in defining any additional impurities. So the message is that the list can be very long. Of course, some of them, most of the time, are nearly always present, not only the CO2. Then looking at the CO2 quality specs, because is the typical question if the CO2 quality specs can be harmonized, or if there are any guidelines. For sure, one starting point is the conditions and the mode at which CO2 is transported, because we have now intermodal capture routes, and we also have different possible ranges of pressure. We can have gas pipeline, dense phase pipeline, or ships. And for each of them, there are different constraints to look for. Then here is a table. I will not go through that due to the limited time, but the idea is that impurities are often, discussed in classes, and they need to be considered all together. A typical example is when talking about the presence of species that can lead to corrosion and can react all together, like oxygen, SOx, NOx, and water. So here the key points are that the focus should not be on the CO2 purity, because the CO2 purity is the balance. The real challenge is to meet the ppm level, often specification on the most critical impurities. Impurities that then must be limited for several reasons, not only technical, but also health and safety, and also there should be the economic part that plays an important role for the deployment of CCUS chain. We know that impurity affect the thermophysical property. We are going to see later a few examples on, especially for non-condensables, and these in turn will affect the technical and economic part. Then, talking about the CO2 specification, again, I will not go through this very large table that comes from, the publicly available CO2 specs from mostly commercial projects, but the idea is to give a few messages. You see that, again, for some of them, CO2 is already reported as the balance, because the real limiting factor are these this list that is here kept shorter. Typically, if you look at the real CO2 specification, is even much longer, the list, because there are several other species that here I couldn't have included due to the lack of space. But for some species, the message is that for some species, specifications are aligned. For instance, for oxygen and for ammonia, they are quite harmonized among the different projects. But for some other, there are still variations that can be of even of one order of magnitude between the different projects. So the question is, well, not only, what are the acceptable compositional limits for a specific project, but if there is a possibility to standardize or to provide guidelines for the impurity limits. Then coming to the non-condensable effect on the physical property of CO2, we have here an overview of the impact on density. So for instance, here we have modeled the density across an isotherm at different pressure for different streams. If you look at the gray one, is the pure CO2, and the message is that when you have contaminant in traces, since density is about properties, their impact on the density is very limited. While then, if you look at the condensable, when they increase and become 1% or even 4% or more, the impact on the density is significant, and this reflects into increased processing, so cost in the purification, but also in the transport and storage cost. Here is another isotherm at supercritical condition, where above the critical pressure of CO2, the deviation, the differences in density is even larger. Then, about phase behavior, as already anticipated by few presenters earlier, we know that we want to avoid multi-phase flow. Either we are in the liquid or in the gas transport phase. We know that impurities affect the phase envelope. For instance, here is the effect of different volatile impurities, so non-condensable. It's clear that starting from the pure CO2, they increase and they may increase even considerably, depending on the species, the saturated liquid line. So the pressure at which we need to work to stay above the saturation for a given temperature. On the right, you see the impact for a given impurity, for instance, nitrogen, in terms of different concentrations. So from 1000 ppm up to 10%, you see a clear shift of the critical point, but also an increase of the saturated liquid line. Then here, a couple of examples that we report are just to show that the topic is much broader than just defining a compositional list, because when designing the processes or when analyzing them from the point of view of process modeling and simulation, even the selection of the thermodynamic model is important. If for pure CO2, is well known that the Span-Wagner model is the reference most accurate one. For mixtures, the choice depends even on the simulation environment, on what is available. For instance, here for the pure CO2, we see that we use Penn-Robinson in the vapor phase is reasonably accurate, but issue starts occurring when we go in the liquid region. That is the typical issue of liquid model. When instead looking for mixture, here is an example of an oxy-fuel type mixture. We see that if available, the OSCG should be the favored model, but then here is a comparison of three different models like the GERG and Penn-Robinson with calibrated KIJ. Again, they are quite aligned in the CO2 compression on a pH profile here, so in the consumption for CO2 compression, then differences arise in the liquid region. Here is some number from the previous example on how much the CO2 compression power increases under the same conditions. So compression from 1 to 64 bar in the vapor phase, then liquefaction, and then pressurization in a pump. Of course, for the mixture, purification should occur in between. You see here that is clear the increase in the specific compression power. Of course, this reflects into greater OPEX and greater CAPEX for processing and transporting and storing the CO2. Finally, here is an example of a CO2 purification unit that we have been designing and modeling with the previous tool. We start from a composition in this example that is the typical from an oxy-fuel process from cement, for instance. This was from the clinker project. And we assume that upstream of it, the impurities that would end up with the liquid CO2 should be removed. So dust, SOx, NOx, acid, all non-volatile species that can affect the CO2 purification unit shall be removed in advance. And then we follow a typical process of the CO2 purification unit with an intercooled compressor that has also knockout drum to remove water that initially was 11.5% and then is lowered down to 2000 ppm. Then to reach CO2 specification in terms of water, the hydration unit and absorption dryer is needed. In this example, we reach this specification. And then we enter the low temperature part where we have the cold box where the CO2 rich stream is cooled down, in this example, to -50, because the temperature and pressure at which you do the and also the configuration of the cold box shall be optimized depending on different objectives. In this example, you see how for a different content of CO2, the CO2 recovery changes as a function of the separation temperature. That is the key variable here. In this example, with refrigeration close to -50 degrees Celsius, we reached 10 ppm of non-condensable level in the CO2 product. CO2 in this example is then pressurized in the vapor phase, but in other example can be delivered as a liquid. Finally, in the off gas, part of the CO2 that was not purified is still remaining. In this example was 96% the CO2 recovery. Again, depending on the target, that CO2 can be further processed or recycled back in order to increase the CO2 recovery rate. The consumption here was 126 kilowatt-hour per ton of CO2. Now I leave the floor to Professor Roland Spahn. Are you there, Roland?
Yes, I am. Okay.
Are you going to share your screen, right?
Yes, I am.
Good.
You should see my screen now.
Yes.
Yes.
Okay. So, yeah, thank you, Manuel, again. Now, what Manuel already pointed out is that we have to look at different concentration levels for the different impurities. Now, depending on the kind of gas we are treating, depending on the capture unit, we typically see impurities in the percentage range. And in the percentage range, we have things like nitrogen, oxygen, argon, or typical non-condensable gases. In the per mil range, we typically see water. And then we have impurities which are in the ppm range, and that's typically components like SOx, NOx, H2S, whatever. Now, the important message at this point to all of you is people are usually discussing CO2 purities, but that's far too simple, because whether CO2 has a purity of 95, 98, or even 99.8% tells nothing about the really critical impurities at per mil or even ppm level. No? So even in 99.8% pure CO2, you can have unacceptably high concentration of water, SOx, NOx, of these components. Now, if we talk about non-condensable gases, many of you will be aware that for pipeline transport, they are critical for operational reasons, but mainly also for the issue of running ductile fracture. That's something Sven Tollak will go into in the next talk, so I won't mention that here any further. What people are usually less aware is that for tank transport, impurities or non-condensable gases have a strong impact on the allowable storage time at medium pressure transport. But these are things that are pretty well understood. We do have good models describing mixtures of CO2 with non-condensable gases. The next issue is water, as I said, up to per mil range in the raw CO2. Now, the phase equilibrium of water and CO2 is very complex. So we do have vapor-liquid equilibria. At higher pressure, we have liquid-liquid equilibria. At low temperature, we are facing ice formation, hydrate formation. But still, all these phase equilibria are relatively well understood as well. And if we look at pipelining condition, we should expect that about 2000 ppm of water in CO2 are acceptable without forming a separate water-rich phase. Now, at low temperature in the pipeline, hydrate formation may become an issue, which may lead to blockage of systems. But this is understood pretty well too. So I didn't want to show the complex 3 and 4 phase lines of hydrates at this point. And what industry is mostly interested in are the limits below which solid phases can occur. And that's something we can calculate. So if we look for gas phase transport, about 250 ppm of water should be acceptable in the gas phase without risking solid formation at typical pipeline conditions. In the dense phase, it's even higher, even more than 500 ppm water would be acceptable. If we talk about medium pressure tank transport at low temperature, ice and hydrate formation becomes a larger issue. So in that range, we could accept only something like 30 ppm of water without the risk of solid formation. If we look at actual specifications given by different storage projects, this is on the left side, it's Aramis. On the right side, it's Northern Lights. You see that for water, the blue circles, well, for ship transport, really the 30 ppm are mentioned. That's what we find to avoid solid formation. But for pipeline infrastructure, we see values which are far below what is possible without solid formation. And at the same time, we see values for components like SOx, NOx, H2S, which are in the ppm range, so very low concentrations. And those are the components which really become cost drivers in CO2 purifications. The reason is, and that's something that became very clear over the last few years, that we have reactions taking place in dense CO2 phases, reactions which we would not expect in that form in typical flue gases from power plants, for example. And these reactions, in the end, all lead to the formation either of sulfuric acid or of nitric acid. And sulfuric acid in particular forms, together with water, a second highly corrosive phase at concentrations which are much lower than the concentrations we have, which we see for the condensation of pure water. Now, IFE in Norway has run extensive tests, very complicated tests, to see where we find dropout of a second phase and where corrosion becomes visible. And the only software tool I'm aware of which is used to predict this is only MSC, which is kind of a black box software. In principle, we know what kind of models are used, but the parameters are proprietary. So it's hard for us as scientists to really evaluate this. But Sonke et al. Compared the results of Oli MSC with their experiments, and only in 19 out of 34 mixtures, they got a qualitatively correct result. We don't have information on the actual composition of the acidic phase. But what is obvious is that we do not have models yet which describe the formation of acidic phases in supercritical CO2 at pipelining or at tank conditions with sufficiently high accuracy. And that's what all the impurity discussion, or most of the impurity discussions now, is about. Actually, this is something we are working on in GigaCCS in a Norwegian project. In CorEU, we are working on a different issue. And this different issue is that we have quite a few components which are not covered by the specifications. So depending on how the specification is written, it essentially says that these components are not allowed. So this is an older Northern Lights specification. And for example, you see that TEC at that time was specified as not allowed. And that's a point I consider critical, maybe not for technical reasons, but for at least for legal reasons, because with new equipment or laboratory equipment, you will find almost everything in CO2 streams in multimodal transport networks. So any definition as zero may result in legal issues later on when there is some damage and people start to ask what has been in the stream and have the specification been met. So what we are looking for in CorEU mostly are means how we can specify limits for components, multitude of components where we hardly have any information on phase equilibria or any experimental data on how they behave in these supercritical CO2 regions. And this is something that's the latest Northern Lights specification now. The colleagues at Northern Lights obviously became aware of this problem. And if you look into the new specification, we have something like 0.2 ppm limit for TEC. So we do have a non-zero value. And that's important. So I frankly speaking, I cannot tell how profound these 0.2 ppm are and where they come from. But it's not zero. And any reasonable limit is better than zero if we define specifications like that. Okay, thanks for your attention. That was a brief introduction into impurities in CO2 streams from our
Many
side.
thanks, Roland. Many thanks, Manuele. There are a few questions in the chat, in particular from Madhvi Agarwal for Roland. How about if we choose high-grade strengths, alloys for piping and tech material? That would offset corrosion due to impurities, cost versus design considerations, if any?
Well, in principle, one could go for high-grade materials, but if you look at the phase which is formed, then you have an aqueous phase which contains sulfuric acid and nitric acid. That's about the most aggressive acid combination we know. So there are hardly any materials which will withstand this combination. Unless you are able to use polymer liners. Polymer liners could withstand, but polymer liners cause problems with CO2, with high density CO2. So choosing materials which withstand these concentrations are, at least for pipelines, I think it's not a possibility. For tanks, it might be possible, but it would be very expensive materials. So I think the right way is to avoid these corrosive environments and not trying to use materials which withstand, unless we get feasible solutions with polymer liners.
Thank you very much, Roland, for the reply. And now we shall move to the next speaker. Coming up, Sven Tolak Munkejord, Chief Scientist at SINTEF for CorEU. The session on pipeline integrity, risk, and venting. Sven, if you're here, the floor is yours.
Hello, here I am. Can you hear me and see the slides?
Yes.
Yeah, thank you very much. Yes, so my name is Sven Tolak Munkejord. I work at SINTEF Energy Research, and in CorEU I lead the work package on core technologies, and I'd like to talk to you about CO2 pipeline safety and the influence of impurities. I'd like to acknowledge my colleagues at SINTEF who've helped me over the years with this, and some of the previous projects, in particular Elegancy, where some of the experiments were done that I'll show you. All right, so I'd like to mention the concept of fracture propagation control. I talk about depressurization of CO2 in pipes, and mention influence of non-equilibrium and of impurities. So I guess this is known to most of the audience, but just to reiterate, by mid-century, several countries, including the EU, have pledged to be climate neutral. We need to use all the tools in the toolbox, including CCS, and globally this would entail the capture, transport and storage of several gigatons of CO2 per year, which, as far as I know, is roughly in the same order of magnitude as natural gas today. So evidently we need a very large system, and it should be optimized and safe. And of course, we have experience with oil and natural gas, but CO2 is different in several ways, and in particular because of the tight coupling between fluid and thermodynamics. In operation, we will be close to some of the thermodynamically interesting points, like the critical point and the triple point, which I'll touch in on, and this gives phenomena like boiling due to depressurization or dry ice formation, etc. And engineers, they need to, when making safe and optimal system, they need models that are experimentally validated in order for them to be able to assign numbers to different effects. Okay, so this slide I borrowed from Roland Spahn, by the way, and he talked about this. So to the right-hand side here, you have the ppm level impurities, which are important to understand better. I won't talk about them, though. I will stay at the left-hand side here with the impurities that can occur in the percentage range and which will affect the bulk properties of the fluid. Okay, phase diagrams, that's interesting. And I don't know about all of the audience, so I'll briefly try to recapitulate here. So for pure CO2, if we plot temperature and pressure, we have a curve here dividing between the liquid and vapor region. That's called the saturation curve. It ends here at the critical point. So critical doesn't mean dangerous or difficult or anything. It's just a mathematical term describing a curve that ends. And down here at low pressure, you have the triple point at which solid, liquid, and vapor exist in equilibrium. Now, if you have CO2 with impurities, as here with 1.8 mol% of nitrogen, then the saturation curve is no longer a curve, but an area, the label 2 here, where you have gas, liquid in equilibrium. And in effect, this results in boiling taking place at a higher pressure than otherwise, and this needs to be taken into account in process and system design. And if you have a very light component like helium here, then this two-phase region becomes very large indeed. By the way, the reason you see 1.8 and 1.9 mol% is that we made experiments with these compositions, and we used helium in order to avoid some of the difficulties of hydrogen, but it still is a light component with some of the same or similar properties. Okay, now for running ductile fracture, what is it? Well, imagine you have a pipeline containing a pressurized and compressible fluid, and for some reason, be it corrosion or third-party impact, a hole is generated in the pipeline. Now you want to know whether the hole stays a hole or whether it will develop into a crack propagating along the pipeline. And in order to understand that, you need to understand the forces from the fluid inside the pipe on the opening pipe flaps, as well as the competition, as it were, between the crack velocity and the decompression velocity of the fluid inside the pipe. Now, if the crack is faster than the fluid decompression, this means the crack will stay always at a high pressure, so it can continue over a long distance. And this is something you want to avoid by using the right steel quality and pipe thickness. Not too much, because then your large system becomes too expensive, and not too little, of course, which would be very detrimental. Trouble is, for running ductile fracture, the state of the art is quite empirical. So in the plot here, this is a variant of the plot that you will find in the DNV recommended practice, where at the x-axis you have a fracture resistance, and at the y-axis you have stress ratio. And the blue dots here are full-scale experiments which propagated, and the crosses are the experiments where you had a rest. And basically you want to divide the two, which is quite challenging. And in particular, when making this plot, you put in the measured pressure, but when engineers want to evaluate a new design, they typically put in the equilibrium pressure, the boiling pressure, and they are not the same. And in addition, this method assumes that it is only the pressure at the crack tip that decides, and that's also a strong simplification. So there is a need to develop a physics-based method for fracture propagation control. At SINTEF, we've worked over some years on a coupled finite element computational fluid dynamics model describing running ductile fracture. And it consists of a CFD model, 1D CFD model that describes decompression and flow inside the pipe and out of the pipe, and a finite element method describing the pipe and the crack propagating. And the way it's set up is that it starts with a given crack width, like here. This crack width is passed to the fluid model, which calculates the leakage rate and the pressure is passed to the structure model as a load, which then decides whether the crack grows, etc., etc. So here we made some what we think is reasonable simplifications in order to be able to calculate industrial scale pipes, but there are things we want to refine, and I'll touch on some of them in the following. But first, some validation we did some years ago for CO2. So I'd like to briefly explain this. So to the plot at the left shows crack speed plotted as a function of crack position. The red dashed line is the experiment, and the black curve is the simulation. And you can see that the experiment has a slightly coarse resolution. This is because of the way that it's done. You attach strings around the circumference of the pipe, and when they break, you know where the crack is. But at least there is a ballpark agreement here. To the left, you see pressure plotted as a function of time for different positions, 1, 3, and 5 meters from the original crack position. And you can see that there is reasonable agreement, although in some of the regions, for instance here, our calculation gives a higher pressure than measured. And one of the reasons for this is that in our model we assumed full thermodynamic equilibrium, which is likely not the case in reality. By the way, the vertical lines here is where the data acquisition system failed because the pipe was hauled out on the moor, so to say, because of the strong effect of the crack. Okay, so now for some further development and validation of flow models. For this, we use data from the Excel depressurization facility, which is located at the Thermal Engineering Lab in Trondheim. Excel, by the way, means the European CCS laboratory infrastructure. And it consists of several labs in many countries. In this tube, it's a 60-meter long tube. It's densely instrumented with temperature and pressure sensors so that we can capture what happens when there is a full bore rupture. There is also a vessel, but I won't talk about it here. Now, at the one end of the tube, there is a flange like this, and we attach a rupture disc, which is fabricated and calibrated to rupture at a given pressure. So for the experiment, we slowly and carefully raise the pressure inside the pipe at a given pressure. The rupture discs rupture, and then we take the data, what happens when the pressure wave travels upstream. Doing that, we can make plots like this, and I'll try to explain. So if you look at the left-hand plot, there are 3 positions at which we measure the pressure. So the blue is close to the outlet, and the 2 others a bit further upstream. There are 3 different fluids here. So the full line is pure CO2, the dashed line is CO2 with nitrogen, and the dotted one is CO2 with helium. And you can see, looking at the green one here, for instance, the pressure drops later with CO2 helium. This means that the pressure propagation speed, or speed of sound, if you will, is slower in the mixture. It also levels off at a higher level, which means that this mixture boils at a higher pressure, as you also saw in the phase diagrams. Then there is an interesting point that I'd like to talk about briefly here on the plot where I show a longer time series. So initially, the full line here for the green one is at a lower pressure, as you can see also to the left, but after 2.5 seconds, more or less, the curve showing the pure CO2 has the highest pressure. So there is an inversion. And the reason for this, in our understanding, is because pure CO2 has a lower pressure propagation speed for a fully dispersed gas liquid mixture, which you have at the outlet. So this means that the pipe with pure CO2 is emptied slower than the ones with mixture. Now, using these data, you can make a plot like this, which is used by engineers for assessing running ductile fracture. It's a bit quirky, but this is how it's done. So they plot pressure as a function of wave speed. This is the speed by which pressure advances with respect to the fixed pipe. So if we concentrate first on the right-hand side, the decompression starts here at 12 megapascal, then it goes downwards like this. You can see here there is good agreement between experiment and calculation. We used, by the way, for pure CO2, the Spahn-Wagner equation of state here. At this point, interesting stuff is happening. So if we assume full thermodynamic equilibrium, then our model tells us that as soon as we have any vapor present, the wave speed jumps down to the value here. Now, instead, if we assume that the liquid would stay liquid, metastable, then we get the green curve, and our data shows something in the middle. So this does not mean that the Spahn-Wagner equation of state doesn't work. It only shows that in this case, the process is so fast that there is no equilibrium. Now, to speak about the effect of impurities, I show you here results from 3 tests. So the blue is pure CO2, then the green is CO2 nitrogen, and the red one is CO2 helium. And it's similar as you already saw. In the single phase, the pressure propagation speed is lower with the impurities. These impurities increase the boiling pressure. And you can also see here, this is in the 2-phase region, the impurities give a faster pressure propagation speed in a 2-phase dispersed mixture. Okay, now if you have a pipeline and you want to consider different operating windows and how will this influence running fracture, it's useful to make a plot like this. So fast decompression will be isentropic, so that's why we illustrate various isentropes here. And you can see on a summer day, for instance, with more than 20 degrees and a pipeline with a low pressure, you can hit the 2-phase region at a higher pressure than for a cooler day and a higher pressure. So in effect, for running fracture, a lower pressure in the pipe can be more severe than a high one, which is counterintuitive until you've seen this plot. Now, for impurities, there are some open questions or that we should investigate more. In particular, how far beyond equilibrium does the process go in order to, because it's so fast that for instance, in this isentrope here, in reality, it wouldn't stop at the saturation, but go a bit below. And in order to find out this, we need model development and also adaptation of parameters with comparing with systematic experiments, and this remains to be done. Also, an open question is when we want to calculate what happens in this 2-phase region here, how do we treat the different components when there is no equilibrium? This is also a question I haven't seen the answer to. And with this, I'd like to conclude that the design of pipelines transporting pressurized compressible fluids, they must be assessed for running ductile fracture. Current engineering methods are mainly empirical, and more accurate design requires the development of models containing physics, including the influence of non-equilibrium on the boiling pressure and pressure wave speed, and also the behavior of impurities in that process. And we need systematic depressurization experiments for model development and validation. And also, these insights will be directly relevant to understand other but similar processes like the flow through nozzles or valves or leaks and the dispersion of CO2 in the surroundings following a leakage. With this, I'd like to thank you for your attention.
Thank you, Sven, for the insightful presentation. And I'm pleased to welcome the next speaker for the session on measuring, monitoring, and verification value chain consideration from EasternLights, Gerardo Villamizar Plata, CIE Integrity Director at Air Liquide. Please, Gerardo, if you hear, the floor is yours.
Good morning, everyone. Am I coming through okay?
Yes.
Okay. I will show. Please let me know if you see my screen, because with this WebEx tool is new for me.
Yes. Yes.
Do you see it right? Okay.
It's not in presentation mode, but we see the slides.
How about now?
Now it's loading. Yes.
Okay, got it. So, okay, I will go through right to the point. This first slide, this is to share with you a message about how many times I have received the question about, is this CO2 specification conservative? Is it relaxed? Is it okay? Is it okay for us or not? Well, the answer is always depends. Depends on what? Depends on the source. Depends on the feedstock. We cannot just by looking at the table of a CO2 specification say and make the conclusion that, wow, this CO2 specification will be an issue for us. Well, we need to see the context. And this is one of the key messages that I wanted to give you today. And in order to do that, I brought some real examples, projects that I will not mention which projects are those, nor the specs, but those are real values. So if we take the example of HCN, well, we have a spec that we all know, I suppose, 100 ppm mol HCN. I put it here in green because if we have 10 ppm in the flue gas, well, it's not an issue. However, if we have lower values as we have in other specs like 2 ppm or 0.5 ppm mol, by having 10 ppm in the feedstock of the capture unit, it is an issue. Another example is H2S. So I brought the same specification, version 2024 and version 25. In the version 24, by having 1.5 ppm mol of H2S in the flue gas, 9 ppm wasn't an issue. When it became 1 ppm, well, it was an issue. So I'm sure you get the concept. Where I'm saying. I put other examples which are not related only with corrosion, but with safety, so like aromatics. So there are several specifications out there. Depending on the flue gas, on the content in the flue gas, the specification may or may not be an issue. Of course, depends also on the technology, on the capture technology, but this example is with a given capture technology. This is why the message is the quality is highly dependent on the source. We cannot conclude only by looking at the product. We need to see also at the feedstock, which brings me to the next slide. And key message here is the industrial setup. Okay, by industrial setup, what does it mean? Means that if you have just focus here on the picture at the right, if you have several emitters here, biomass, blue hydrogen, power generation, other industrial sources, you have the pipeline, and then you may have two different options, okay? So you may have a liquefaction terminal to put CO2 from dense phase or gaseous phase, whatever, into liquid storage and into the ships, or you may have no liquefaction terminal at all and just going directly through a pipeline onshore and then offshore. Okay, this is a critical component, the liquefaction terminal. Why? Because in this case, you may end up having two different specifications: the ones for the pipeline before the terminal and the ones for the liquid CO2. So the key message here is we saw in the previous slide the CO2 specification. The criticality of such a specification depends on the source, but also depends on the industrial setup, which means that a well-defined CO2 specification must include not only the values of impurities, but also the conditions where this specification has been defined, which means operating conditions, operating temperature, pressure, liquid, dense, gas, phase, other. Okay. And moving forward, in the case of liquid CO2 projects, then defining the boil of gas composition is also a must while defining the liquid CO2 specification. Why? Because we may have cross-contamination, for example, in the ships. The ship may come from other plant, may bring ethylene or other impurities, and this is why, while setting the liquid CO2 quality requirements, it must come with the boil of gas. Okay, so it's not as just a table. That's the key message that I want to bring today. The data modeling, I think our colleagues covered that topic today. It is required to have a well supported software. Why? Because it will help us, the industrials, to predict what is going to happen in the asset, in the pipeline, in the storage vessels, in the spheres. Okay, so this is critical, and it will also help to save time while defining the test matrix, because if we can predict, well, it will save money and time while running the lab tests. And another key aspect is the CO2 standardization process. Well, the key message here is that we really need to have a balance. We need to base all our specifications based on scientific facts rather than fears. We cannot set a CO2 specification just in case. We need to have lab tests that support those values, and really avoid, because I've seen that they copy paste the specification. We are just copying because somebody else from 100 tests, well, it should be right, then I take that value. So we really need to be careful with that, and really having the rationale behind of those limits. Why 1.5 ppm of NOx? What is the risk? Why 0.5 ppm of BTX? What is the risk? This is key. And again, I insist a lot, because if somebody forgotten the mandatory ship return gas specification when it comes to projects involving liquid CO2. And key message and conclusions also here. So again, this is always a balance, and when it comes to balance, we need to talk to measurement. And measurement, it's really critical, because not only impacts capex, but impacts also the contractual framework. And having specifications in the table as not allowed, balance, zero, or just families are simply not acceptable. You cannot measure balance. You need to measure 99.99, 99.5% mole of CO2. You cannot measure balance. So it may work for a scientific work, but for industrial projects, it doesn't work. It's as simple as that. We need to have values of the impurities and the CO2 in order to contractualize an industrial project. Okay, so this kind of wording are simply not acceptable nor workable, not real. Okay, families, what is the issue with the families? Is because we cannot measure aromatics. We need to measure something that represents the family. So we need the breakdown. We need, when it comes to total sulfur, we need the sulfur speciation. We cannot just measure just the family. Okay, so this is critical. The second point is the CO2 specification must list all the components of concern. Okay, we cannot just say here we have the 30 impurities, whatever is not listed is not accepted. It's not possible, because when you are burning animal waste, tires, COVID masks, and all those kind of things, you have half of the periodic table in the flue gas. So it's impossible, not realistic, saying whatever is not in the table of the CO2 specification, we cannot accept it. We need to communicate the emitter, the capture technology owner, and then the sink. All the actors in the CCS chain need to communicate and to work together the CO2 specification. Of course, the public CO2 specification is the baseline, but as we saw, is highly dependent on source. It's highly dependent on the industrial setup. This is key. And well, as final conclusion, I wanted to give you the takeaway. The CO2 product specification is a function of a well-defined flue gas composition, so the feedstock to the capture unit, the industrial setup, defining applicable operating conditions. So I want to see that in the table, those conditions. The realistic analytical solutions consistent with the proposed CO2 spec. Okay, we cannot just say 0.1 ppm NOx. Maybe there is something that is no technology available to analyze that. The scientific sources, so linked with what I mentioned before, CO2 spec defined based on facts, not on fears. And specifically the case for liquid CO2 projects, a well-defined boil of gas specification. Thank you.
Thank you, Gerardo. Just checking if there are questions in the chat. Okay. So I do not see any questions. I think all the presentations so far have been super clear, and pretty happy about that. Many thanks to the speakers for this.
Well, I hope I
first,
see several
session.
known names that are connected, so I hope it's clear.
Okay, so we have a first question from Lawrence Lechner. Whom would you see as competent authority to moderate the specs in the CCUS chain?
Well, who's the entity who defines the CO2 specification? Most of the times is the sink, so it's the final user. Okay, or maybe the intermediate pipeline user. Okay, those are the entities who are interested that everybody that is sending the CO2 into the hub are compliant with the CO2 specification, because otherwise we'll have corrosion or safety issues, whatever the risks are. Okay, so those are the main interested on having a compliance in the CO2 specification. But again, a CCS chain is a chain of different bricks. So to me, the key of success for this is a real transparent discussion, a joint effort between all the bricks in the chain, because everyone has an interest to make the project fly and to make the project alive. And I have observed that several times in the last years with industrial projects. The success is really this joint effort, this joint collaboration of building a specification that is safe, but it's also realistic, and it makes project fly. That doesn't kill projects. This is key.
Thank you, Gerardo.
Prego.
Okay, so at this point, we have scheduled a short break, 5-minute break. However, for those who would like to stay, there's an interactive moment in which we're sharing to the chat a Miro board addressing one of the biggest questions. What is the most underestimated impact of CO2 impurities in your work? So during this 5-minute break, if you want to have a coffee, have some water, stretch your legs, or prefer to stay, just do whatever you wish. We shall reconvene at 11:07. So let's have this short break, and we will be back in 5 minutes.
Just one last thing, Gerardo, if you can exit the presentation mode. Oh, it's okay.
See you in 5.
Sono nel baule e il pianale è a posto. Ciao. Hai visto? Abbiamo anche la cappelliera. Il pianale sono pure le cazzo così.
Okay. Now, as people start to reconvene slowly, I will start introducing the second part of this webinar related to trade-offs, cost impacts, and operational optimization. So for this first session of three, basically, I'm calling CorEU representatives Yangshu Wang from Natran RNI and Chao Fu from Sintef Energy Research for the session on optimizing CO2 purity, the engineering cost balance. If you're already here, please, the
Yes,
floor is yours.
I'm sure you can hear me.
Yes.
And my presentation, it is good.
Yes, but it's in not in viewer mode. It's in it's in presentation mode, but not in the proper way.
I will do it. It is good now.
No, it's still
So I will stop
switch
it.
it.
Yes, I will present it, but it's a little bit complicated. Show the. I'll show the. Just test it before, but maybe it can. Yeah, it is good.
Yes.
It is good. Are you sure? Because
yes,
yes,
confirm.
That's perfect. Perfect.
it's perfect. Okay.
Yes.
Thank you for introduction. My name is Yanshu Wang. I work for Natural Research and Innovation in France, and we will share this session with my colleague from Sintef, Chao. So the basic idea is that I will give you a brief introduction for this section, and then my colleague Chao will give you a concrete example. So, so just for a general introduction for the CO2 value chain. So the idea is that CO2 will be captured, also purified, and then will be reused or be stored safely and permanently. And our company, Natran, our former name is GRT Gas, is a French national natural gas pipeline operator. And our mission, and we are working for the future CO2 network in France. And our mission is to deliver the unspec'd CO2 to the next segment. And to give you some idea about different modes of CO2 transport, I will use our company's project as an example. So we are working for 3 projects of CO2 network in France. So the first decoupled and CO2 link is related to the northern part of the France. The idea is that we will collect CO2 and transport via online pipeline, and the CO2 will be then transported by offshore pipeline with a Highway Europe project. Another project like CO2, we are concentrating the western part of the France, and the CO2 will be collected and transported by the online pipeline and then transported by ship. So here we have some idea about different mode of the CO2 transport. And now we talk about the purity. So the first idea is that the purity is not a checkbox. It's a system-wide cost and a risk level. So we have seen that the CO2 influx in the pipeline, in the CO2 value chain is never pure. There's always impurities and will give different impacts. And in this section, we will concentrate on the economic effect. That is to say, how do we do the best choice, the trade-off between the different specifications. So the first idea, I think that the trade-off is not as simple as to make a choice between one stricter spec or one looser spec as shown here. It's a very complex decision. We should consider, of course, technical consideration, technical aspect, but also economic aspect. It depends on the economic model. It depends on also organization issues and somehow political issues, etc. It is a very complex decision. But generally speaking, if we focus on strict respect, we will reduce the risk, but we will raise the cost, potentially also especially for the purification step. And if we choose the lower respect, we may have a higher tolerance at the capture plant for the purification, but for the pipeline transport or other mode of transportation, we may have some corrosion issues, tighter operating envelopes, or possible flow assurance issues. And I think the idea for this section is that, or the main idea is that the optimization is project specific. There's no method, one method works for every situation. So to illustrate that, I can show you just 2 examples. So the Northern Lights project, I think, is a well-known project. The CO2 will be transported by ship in a liquefied state with a concentration higher than 98.8%, compared with another project, Highway Europe, I just mentioned. So CO2 will be transported by the offshore pipeline in dense phase with a concentration a little bit lower in 96.2%. And we compare the capture or the purification step. The purification cost, of course, it depends on CO2 purity level, but it is most sensibly dependent on the impurity thresholds. That is to say, if one group of impurity threshold is extremely low, there will be a very high cost associated with that. So my colleague Chao will just illustrate this idea in an example afterwards. So if we talk about the impurity threshold and the cost associated, they are all project specific. There's no method, no general estimations works for all projects. But generally speaking, a higher CO2 purity level corresponds to higher purification cost. I think that is very easy to understand. And now if we look about the transport step, so the transport cost, it depends, of course, on the mode of transport and in which state, by which mode, pipeline, ship, etc. And they are also project specific. But generally speaking, a higher CO2 purity level corresponds to lower transport cost because CO2 is well treated before. So here, the idea is that if we shift the spec, if we pass from a looser spec to a stricter spec or the inverse direction, we shift the spec, we will shift the cost and risk from one segment to another segment. We will not remove them. And in a project point of view, or in our whole CCUS chain point of view, value chain point of view, the best solutions are always there to achieve the balance between the engineering robustness, that is to say, the technical boundary, with the economic reality of this project. So I think from this point of view, some important information to deliver. The coordination between different segments of the value chain is important. It is also important to develop the project through partnerships and create synergies. That is what we are doing today. And also, it is also important to conducting tests to verify and validate technical tests, the specifications that we want. So I will now give pass to my let my colleague Chao to continue the presentation to give you a concrete example. Thank you.
Oh, thanks, Yanshu. Do you want me to share? Can you share? Or
you want
so
to? Okay.
Yes, please just avoid this time.
Yeah, I will share. No problem.
Thanks.
So.
Yes, next, please.
But it's still in the speakers mode, so could you maybe enlarge it a bit?
Yes, there will be a little issues from my. It is good for you?
No, it's still the same. Now it's better.
Now it's better?
Yeah.
Are you sure?
But it's still not full mode, but at least it's bigger.
I think it's okay now. Can you move to the previous slide, one slide before?
Yeah.
Okay, thanks. So I'm going to introduce our work on this CO2 condition in the CorEU project. So we have already talked lots about this CO2 impurity source and the specifications this morning. So the question is that how to get from this CO2 source with these different impurity levels to this many different specifications. So the question, which purification technologies should be used if we for given CO2 impurity and for the given CO2 specification, and what are the energy penalty and cost? That's something we want to understand. I'm not going into these details because we have already heard lots of things this morning. Move to next, please. Yeah, sure. Yeah. Okay. This slide is a bit busy. It shows the available technologies for deep purification of those impurities. We have for this project, we are not expected to cover all the impurities, So we have identified some kind of we call it critical impurities to be studied. For example, NOx, SOx, these acid gases, and also the atmospheric gases. For example, for nitrogen argon removal, as far as we know that low temperature phase separation is only available technology to remove. And if you want to get to this sub-ambient low temperature process, you need to remove the water to control it down to 10 ppm. So you need this refrigeration process also. So what I'm trying to say is that the technology selections, they may be interconnected. And for oxygen removal, you can do this low temperature flash distillation. Again, you need to control the water down to 10 ppm. And if in order to control the water to 10 ppm, you need to use molecular safe dehydration technology. You can also use this catalytic oxidation. And for this technology, you need to heat up this CO2 and to prior remove these particles, these chronates and sulfur. And in addition, you may introduce new impurities like the reductant, not reacted, and water. So, which means the sequence of impurity removal should also be considered, because you probably don't want to have a dehydration unit first, and then you use this catalytic oxidation, and then you introduce the water again and do the deep removal of water again. You may also use this deoxygen from solvent or chemisorption on metals. And for water removal, we know that we can use compression condensation for preliminary removal, and we may use TAG, Cynic G, or molecular safe. All these three dehydration methods, you need heat supply to do the regeneration and to reach different level of water removal extent. And for SOx removal, you can use the wet, dry FGD, caustic DCC, direct contact cooler. For NOx removal, you can use SNCR, SAR, which is quite conventional, and use this caustic direct contact cooler or this low temperature NOx. That's presented in literature also. So for this,
just a quick one.
okay.
Sorry. Have you been able to upload your slides on Moodle for Monday?
Is somebody not for me, right?
Yeah.
Okay. Sorry. So the operating conditions and the integration should also be considered. You have this heating requirement. You also need to optimize this operating pressure, something like that. Okay, next slide, please. I think I need to speed up a little bit. Yes. So let's take an example for this oxygen nitrogen removal, use this low temperature phase separation. So these two figures shows the low temperature separation, use either two-stage flash on the left or use this distillation. So in both separation process, we do the compression and condense out the water, and then we have a dehydration unit to deep remove this water and then enter this cold box. And on the left, we use two-stage flash, and on the right, we use distillation. And the distillation process layout, to some extent, is more complex, and these two are used for shape transport. Next, please. I just use this two-stage flash as an example for, and this is a bit small here. So this two figures shows if we remove oxygen, use this two-stage flash. So the question we are going to answer is that for different oxygen in the oxygen level in the feed stream, for example, 500 ppm, 300 to down to 20 ppm. And if we want to reach these different specifications, what are the energy consumption and how the CO2 recovery were changed. For example, if you on the left figure, if you have for the blue curve, if you have this 500 ppm in the feed stream, if you want to control to down to 50 ppm, then it's you have the CO2 recovery rate around 87%, which means you will lose 13% CO2 here. And we know that for amine capture, normally we use 90% CO2 capture rate there. You already lost the 10% CO2 there, and I don't believe we want to lose 13% here also. So normally we want to lose the CO2 as less as possible in this CO2 purification step. So for example, if you want to control the CO2 recovery rate to 99%, which means you lose less than 1% CO2, then if you want to use this two-stage flash process layout, if the oxygen feed stream is 500 ppm, then you can only use this two-stage flash control to around 300 ppm. And if you want to achieve this 10 ppm oxygen level as specified in the necessitates specification, then the feed stream should be limited, oxygen should be limited to 20 ppm. And the right figure shows the specific power consumption. This is really the change mainly due to the different amount of CO2 recovered. And this CO2 loss is directly related to the increase of the cost of CO2 weight. And the next is my last slide. Next, please, Yanshu. Yanshu?
Yes.
Oh, sorry, it's here now. Sorry. Yeah. And this, again, these two figures similarly shows the nitrogen contour. So I'm not going into the details again, but basically, again, if you want to achieve 99% CO2 recovery rate, so if you have 2000 ppm in the feed, then you can only control to around 950 ppm use this two-stage flash. And if you want to achieve this necessitates specification 50 ppm in nitrogen level, then the feed stream should not be more than 100 ppm. If it is more than 100 ppm, then you should not use this two-stage flash. You probably should move to the distillation scheme. And this is for the pure impure, only one single component. If you have a mixture of oxygen and nitrogen, then you can use these curves to get two different CO2 recovery rates. And then the actual CO2 recovery rate corresponds to the lower one. And I have one example, two examples here, but I just show one or explain one here. If you have 300 ppm oxygen purified to 180 ppm, and another one you have 500 ppm nitrogen purified to 150 ppm. So based on these curves, you can get 99% for recovery rate for oxygen removal and 98% for nitrogen removal. And the actual capture rate would be 98%. Yeah, I think that's all what I want to share. And in this CorEU project, we are also work on this destination and also to work on this to cover some other impurities. That's what I want to say. Okay, thank you.
Thank you both, Yangshu, Chao, for this insightful presentation. Just checking if there are questions for you on these topics in the chat. Otherwise, I will move forward. Okay. So, I do not see any questions in the chat. Thank you both. So for the next session, I would like to, on risk operability and performance, I would like to call the technical leads from CorEU and ENCASE, respectively Dr. Jens Erfurt from Open Grid Europe and Christoph Proust to open their mic. And as we would like to have an open discussion about several items, we have prepared some questions just to break the ice, but we would like to nurture the discussion. So I will start with the first question related to where do we already have robust impurity thresholds and where do we still lack validated engineering limits? So who would like to go first? The floor is yours.
Yeah, I can make a start and I can try to start with the simple stuff. I would argue that we have a validated limit already at the minimum purity, at least in pipelines. So from a technical point of view, a pipeline doesn't need any high purity. So the 95% that can be derived from the London Protocol, if you want to store the CO2, those are in place. I would argue you can work with that. If you are talking about tank transport, as we have already seen on several slides, the minimum purity requirements are higher, a lot higher, for thermodynamical reasons. So that's, I guess, the easy part. So, and as to where do we still lack validated engineering limits, I think the big issue here is acid corrosion. That has also been mentioned before today. So what that means in practice is that you need a set of limits on the big five: oxygen, water, H2S, NOx, and SOx. And that is still very much subject to research, very difficult research, I might add. And the problem with that is not so much that we have no idea how to avoid acid corrosion or to avoid the formation of acid from these five molecules. It can be done, and there is a set of limits. Some sets of limits are known that where acid corrosion can be avoided. The problem is basically costs. And we do know that acids are created from a complex interaction between these five molecules, but we do not know how to set a limit that actually leads to the lowest cost, because the precise interaction is not fully understood.
Well, I do agree with what Jens was saying. Basically, yes, we have doubt about the coactivities of those impurities, and even with CO2. And we have another aspect which has not been treated so far, which could be a problem, is the toxic aspect. If there is a leakage, because it's not only corrosion. If you are going to the fires from accident on the methane natural gas pipeline, which are nearly the same structures and nearly the same pressures. Most of the leakages, especially the massive one, are due to aggressions, mechanical aggression on the pipeline. So it's not only corrosion. And in this situation, we have to consider the size of the cloud, if there is. such a leakage. It could be quite large. And we are a bit worried about the choice of the toxic limit for CO2 in order to protect people, to organize the rescues. And it seemed that this limit in terms of threshold is about 3-4%, something like this, from existing accidents. Much less than we thought. I mean, 10 years ago, for instance, we were more at nearly 10%. And if this is so small, then there is a question about the impurities into the CO2, which come and have a coactivity into the toxic threshold. So I do not mean that it is sure that there will be a coactivity for the toxicity outside in case of a leak, but we would have to address this at least openly at some point. But for the corrosion aspect, which is another added possibility, internal corrosion, for a total rupture of a pipe, yes, I do agree with Jens that we have identified at least the major species playing a role, even if we are still lacking adequate modeling, as if you remember, Roland talked about.
Thank you. I think there are questions in the chat or questions in the audience. So please open your mic and you can pose directly the question. So I think Harun has a question, as I see the raised hand. Please, Harun.
I'm yes, can you hear me? Right, thank you.
Yes.
Thank you. I'm sorry, I don't want to, I'm not trying to hide, I just can't switch my camera on, but anyway, thank you for the very interesting presentations. One thing that has, you know, that I think, you know, that I think needs to be considered is that the impurities, that the thresholds that we are talking about are during normal operation. And if we have a situation where we are looking at a cluster and we go off spec, for example, you know, we can have significantly more SO2 or H2S than actually permitted into the system. You know, it can happen. You have several emitters, the purification may not basically work or shut down, or some issues may occur. And have we considered that those sort of eventualities? So it might, you know, there are certain components which can cause serious hazard safety implications, for example, to SO2 and H2S, for example, in case they're exceeded. Do we need to make any consideration for those eventualities? I don't know what any of the speakers, if they have any thoughts about this.
Not sure I understand correctly. Are you talking about other than normal operating
Other
conditions?
than normal, yes.
Yeah.
Other than normal, because we are relying on everything working properly and producing the type of purifications that purities that we want. But it is quite possible if you've got several emitters, then something goes wrong and then we have issues.
Yeah. Yeah, a question that was asked earlier today was, you know, if acid corrosion or acid formation is such a problem, couldn't we just make the pipe out of different material? So in the scenario that you're talking about now, that would certainly have an advantage. We could basically afford some emitter tripping, a surge of water coming into the pipeline, SOx levels being exceeded. So if we had a corrosion-resistant alloy as a pipeline material, we could catch that up far better. But as Roland already pointed out, there are other difficulties associated with that. One more thing that I might add, going back to Sven Tollak's presentation, we do not have any corrosion-resistant alloys for pipelines that are designed against rolling ductile fracture. So that's one problem that we're also facing. But ultimately, this whole issue of some emitter tripping, thresholds being exceeded, I think that's not so much a research topic. Although the exact impact would certainly be, should be subject to research. I think it's something that's being discussed right now very intensely in projects. I think that's more of a contractual thing. One approach to go about it, for example, could be, okay, one of these emitters injecting into the pipeline is exceeding the threshold. But then when you're blending with the CO2 that's already in the pipeline, everything is fine again. So that's something that you could tolerate in operation. On the other side, that creates a free rider problem. You certainly don't want to have another spec for that one emitter and tolerate exceeding the limits permanently. The very complicated topic must be addressed, but not exclusively on a contractual basis. And also research, of course, would be welcome to investigate the exact impact of those surges. What kind of dynamics would that lead to? And that's the topic that's also been broached at some point earlier, reaction kinetics. What do we know about those?
Yes, yes.
Yeah, maybe I can give a comment. Not sure if you hear me. But so my name is Sander de Kruijf. I work for Portos project in the Netherlands. And the question is, if you have a client which exceeds some of the limits of components, you can automatically shut them in based on the analysis results. So what our approach will be is we will continue monitoring the components coming in, and if they're off spec, there will be an automatic shut-in.
Yeah, but that relies on highly effective real-time measurements. And
Understood.
Of course, if you have, and which I'm not sure how easy or difficult it is, as you're alluding to. And the other problem is that, yes, there is dilution, but the problem is that if you have one of the emitters which has a very high contribution to the total flow rate, and that goes off spec, so that's going to be even more of a problem. So not just having a system which can automatically and very quickly react to things going off spec, also we need to have a proper understanding of the dynamics of how simulate through simulation, for example, as to what happens in eventuality that an emitter with a given flow rate goes off specification. How long will it take to have an impact on the overall flow, how the concentration is going to change with time, and where the strategic monitoring device, where sampling. We also need sampling.
Yeah, correct.
On the pipeline.
But what we talk about, these are online analyzers.
Yes, online
and
analyzers.
There's a residence time on how long it takes to get a number from the analyzers.
Yeah.
And you have to take into consideration the pipe length, so you can still shut in the system before the different mixtures are coming together, and you can have an issue with corrosion in that sense.
Yeah,
I'm not saying it's an easy thing to do, but
and
that could be an approach.
Yeah, and it's not just corrosion; there is also safety aspects. Some of these
yes
mentioned.
Yes.
And yeah.
Maybe Arun, we know each other very well. I think it was too early along the last 10 years to investigate all those safety aspects because too many unknowns. But possibly now it could be possible, because all of these projects we are talking about today, to envision a global safety analysis of a network. What is important? What is the importance of the transient? We're talking about the transient. I would also consider the stratifications of the different streams in order to find what is important and what we could achieve in terms of control. It should be possible, because as you are aware about, possibly there is a very important development of biogas injection into the standard natural gas networks, at least in France. And there are multiple players, stakeholders, injecting their biogas from very large farms, for instance. And there is a control and there is a management of the network taking into account this biogas, which could be very corrosive, as you know, because H2S is a biological compound and which has been removed for sure. So there is some example, but possibly, of how we could do this, but we had to know much better the different important aspect that we talked about today and how the system would exist. And I'm not pretty sure yet on what could be the latest configuration of those CCS networks at the European scale, possibly at the European scale. This is my comment on that.
Thank you, Christophe. Thank you, Sander Harul, for this. I'm seeing that there are questions in the chat, in particular one related to, I think, the discussion that Jens anticipated and Christophe commented later, along the lines that could pressure variations along a pipeline, decreasing probably, would have an impact?
Yeah, sorry, Nathalie Brix, it's me that I put this question. So yeah, I understood in some cases that between the injection point of the emitters and where you go, meaning a hub or whatever, next use or whatever, there could be some pipeline variation. And it's not surprising there is some delta P around the pipeline. What is there in terms of impurity, what we should consider, the higher value of the pressure or the lower value of the pressure? Because then we saw that the impurity can change there.
So if we're talking dense phase transport, there's probably not much of a difference. The specifications that are out, so those tests have been done mainly at IFE. If you consider a dense phase pipeline transport, for example, we're talking about pressures of up to 200 bar. The tests at IFE have mainly been carried out at around 100 bar. So I would argue that, especially with respect to acid corrosion, that's conservative. I don't think the effect is much pronounced. I don't have any numbers on that, but I would argue that solubility probably decreases. Solubility of acids probably decreases with pressure. So I guess you're on the safe side if you consider polarity of the CO2 and how it might change in detail at 100 versus 200 bar. I guess you're right to carry out these experiments in dense phase, but at relatively low pressure.
Maybe I could add a physical aspect, perhaps. Okay, with the impurity, but it's a problem when you are running into a bubble of gas appearing somewhere, and then you are repressurizing abruptly, and then you have very big spikes of pressure. We are investigating that in ENCASE for the time being. We experience that in our experience at INERIS here. Experiments, we had burst of pressure like this. It has to be investigated. It's like a water hammer system, so it's not that a mystery, but we needed some measurement and some modeling on that. It seems to be workable, but we have to look after this. We should remain in the liquid phase. We should really remain it. So this will be a verification on this. This is part of the global safety aspect, yes.
Questions on that. Do you observe when you're repressurizing? So let's say the pressure is lowering, you get a two-phase flow in whatever vessel you're using. Mm-hmm. And if you're done repressurizing, do you observe a change in the composition of the different phases? Because all the non-condensables, they should go to the gas phase once it forms, right?
Yeah, we are not sure about that because where it happened, it was quite far from the injection point, and we think at that point we were under pure CO2, but not totally sure. But the possibility that we have impurity will change this. We are not at that point in research. It will change this, certainly, because it changes the dynamics of the phase changes and the sound speed, for instance. So it will have an influence, yes. Very interesting point.
Thank you. We are having additional questions in the chat. I'm not sure whether to pose them now or wait for later. But there is one from Giuseppe Raso stating, when considering liquid CO2 transportation by ship, one potential source of contamination arises from boil-off gas and the gas displacement that occurs during the ship loading. Since the BOG is routed back into the process, it may introduce impurities into the liquid stream. Is there a common approach or set of guidelines from Northern Lights or other players that define how to manage this issue?
Jens, do you have an answer on that?
I do not know how Northern Lights do it, but generally I believe that problem has been recognized. It's a problem that's not specific to, it's not a new problem, let's say. I mean, CO2 has been transported in tanks for a very long time, but that was mostly food-grade CO2 with a very high purity. And if you then need to refill before your after your return trip, you could just vent. Yeah? So that's not, of course, what we have in mind. If we want to build a value chain, a supply chain, that issue with the vapor return must be addressed at some point. I do not know how this will be handled. I guess we will have that kind of enrichment of non-condensables up to a point, hopefully. I do not know how exactly it would be solved ideally. I think it's very much subject to some technical optimization because I guess some emissions, not just of CO2, but also concentrated air contaminants, pollutants, might be inevitable there. The only thing that I know that from a regulatory point of view will play a role here is the taxonomy, which says that in a CO2 transport chain, a maximum of 0.5% of the CO2 must be emitted for the whole supply chain to be considered sustainable. I cannot say for sure, though. I haven't done any math on that, if that is exceeded currently or how that might be optimized. If someone is here from Northern Lights or someone else competent enough to weigh in here, you're more than welcome.
I'm not sure to be super competent, but that's not a very low level compared to what we can lose along a complex value chain. So if we stay on pipeline, it might be possible, but each time you will plan to liquefy, regasify, transfer, etc., the losses, even if you try to minimize it. So that's a quite tricky part. So thank you for taking the attention of this taxonomy, because that was an unknown level for my side.
Yeah, there might be some other part to it. As we've said before, a pipeline only requires a minimum purity of 95%, and it might be economically beneficial to actually stay that low, unless you come to a point finally where you say, you need to remove those acid-forming components anyway, and high purities will be a side effect of that. I don't know. But if we have at some point in the future a system where you transport 95% pure pipeline CO2 and then come to a shipping terminal where you need to increase the purity to say 99.8, there will be emissions associated with that. And it's not clear to me, at least from the taxonomy, how that will be handled, if that terminal will be considered part of the transport chain, or might be something else altogether, like a CO2 production facility. That might be one way to look at it legally.
Correct.
But I think that's something that's, to me, unclear. It might even be an obstacle to FIDs, to multimodal FIDs, which the regulator actually wants, which the Commission wants. Yeah, thank you for the question.
Okay. There's one last question that we gathered from the Miro board chat. So basically, beyond the CO2 specifications for surface facilities, what are the key impurities thresholds that must be considered when injecting CO2 into geological storage formations from both a technical regulatory standpoint? I will put it in the chat. If any of you would like to would like to take the floor to answer that, otherwise we can move forward.
I'm not a storage expert and no geologist, so.
No, not me either. But I know that the main concern was about the pollution of the drinking water. But I'm not sure that it will be, in fact, that the CO2 will be really stored onshore. For safety reason, I'm quite sure it will be offshore. So if it is offshore, the problem is a bit different. Possibly it's about the dissolution of what is into the aquifer, and in case of leakage of this storage, then we are moving from the ground something which could be toxic, as we know. It is more this which is in line, which is being studied by specialists on, in reality. If there is some specialist in the audience, it would be interesting to have their input. I'm not competent on that.
Yes.
Whoops. Yes.
Sorry, yeah, I was on the wrong microphone. But I need report here from IFE. I will touch a little bit upon this on my presentation later in this session.
Okay.
On the whole, I think there's research to be done on the impact on geology, but it's also been largely disregarded because the impact probably is fairly limited. Most minerals that you find in the siliciclastic reservoir, so a sandstone type reservoir, are going to be quite stable chemically. Things may be more interesting in the Middle East, where they're looking at injecting into carbonate limestone reservoirs. So there might be a bit more work to be done. But I can touch upon this a little bit more in my presentation.
One interesting thing that I've discussed with respect to underground storage is the oxygen level. Some 2 years ago, we had some extensive discussions in a standardization context about whether or not the oxygen level, the permissible, should be 10 or 40 or maybe something in between. 40, of course, would be cheaper and would be mostly achievable in amine scrubbing, for example. So that's one number that people put forward. Another number was 10 ppm, because apparently from an empirical standpoint, that's what works in most underground storage sites. If you go above that, or if you increase the oxygen, there might be a risk that you get bacteria growth that are, there are some bacteria that are consuming this, which can lead to clogging of certain formations, porous formations, for example. It looks to me like that is not so much the question anymore. If you consider the pipeline specification or a tank specification, the stuff that's currently known to be safe, you don't go to 40 ppm of oxygen anymore. So you're more at 10, and I think we might even see lower values, because that seems to be promising to reduce the oxygen to avoid acid formation. So I think oxygen is an issue that might be solved for pipeline transportation and might then not be an issue anymore for underground storage.
Yeah, I may add on this issue. I Yes, agree with please. Jens that oxygen might be a concern for clogging by biofilm growth or whatever. In general, my impression is that the specifications for storage are much more lenient than for transport because I mean, I take for granted that we are going to use a high chromium stainless steel, whatever, because we work in high salinity. Once you mix the water with the CO2, you are going to have acidity. So the acidity of the CO2 itself, which would bring the pH down to 3 point something, together with the salinity, that itself is highly corrosive. So yes, so we need to use high chromium stainless steel. So I take for granted that the problem with corrosion you have in transport pipes is because you cannot think of building a 100 kilometers pipeline of high chromium stainless steel. But so in general, my impression is that for storage is much less of a problem than it is for transport. Thank you, Jesus. Fortunately, we have to wrap up this unconventional panel session. Thank you for the speakers that have been engaged so far. And now we have to move to session 3 on operational de-risking and on-site implementation. For the first session, I'm welcoming representatives from ENI and SNAM on the session called Managing CO2 Impurities, Design and Operational Insight from Ravenna CCS. So please.
Yes, I will share my screen, but
okay, thank
Francesco Rebaudi will start with the presentation.
Okay,
Tell
thank
me
you.
if you can see.
Yeah, thank you, Elizabeth. This is Francesco Rebaudi. I'm part of the SNAM CCS coordination team. In this session with the colleagues from ENI, we are going to provide some insights about how we are dealing with CO2 impurities in our flagship project, which is Ravenna CCS, considering both the design phase and the operational one. After a brief introduction about the Ravenna CCS project, we are going to cover both the transport segment and the storage one of the CCS value chain. Well, about the Ravenna CCS project, we are going to invest a couple of minutes because so that we can better contextualize the next parts of the presentation, which are more technical. The Ravenna CCS project has the main advantage to build the reception and storage infrastructure in Italy. It is being developed by the joint venture between ENI and SNAM. It is a paritatic joint venture where ENI is the technical operator. It is being developed in phases. Phase 1 was launched in August 2024. In phase 1, we captured and stored 25 kilotons per year of CO2. It has been a success, phase 1, and we are going to provide some details in the second part of this session. With phase 2, which is the industrial phase, large-scale phase of the Ravenna CCS project, we aim at store 4 million tons of CO2 per year within 2030, and then we are also designing further expansions of the infrastructures to reach a final capacity of 16 million tons per year, exploiting depleted gas fields in the northern Adriatic. On a commercial level, I want to highlight the fact that the demand for CCS storage capacity is very high from the market. There are, of course, many industrials in the area, and unfortunately, a low amount of storage projects under development in the Mediterranean area in comparison to Northern Europe. To get more in detail about what is included in the project, maybe next slide. Okay, the Ravenna CCS project includes the Ravenna Hub, which is a reception unit, a regasification unit, which will receive the CO2 coming from in liquid form, coming from ships from other European countries of the Mediterranean area, France, Spain, Croatia, Greece, and so on. So this Ravenna Hub, which is located in the Ravenna Harbor, will receive the CO2 coming from ships, trains, and trucks. Then there is the Casal Borsetti compression station, which is the place where we are going to compress the CO2 towards the storage facilities. And of course, the Ravenna CCS project includes all the offshore facilities necessary for the storage of CO2, offshore pipelines, platforms, equipments, wells, and so on. In parallel, SNAM is developing the transport infrastructure in northern Italy, a network composed of pipelines, which will be developed in phases. The first phase of this network is currently under permitting. We obtained big news last month, a positive environmental impact assessment for the first part of this network, which will be developed in phases in order to connect the industrial cluster of northern Italy and in further expansions also other European countries. In this network, we are also planning to repurpose an existing pipelines, which is currently used for the transport of natural gas. We are going to convert it for the transport of CO2. Now I can leave the word to my colleague Matthias, who will provide some technical insights about the repurposing and about the management of CO2 along the transport infrastructure. Thank you.
Thank you very much, Francesco. As he mentioned, I am Mattias Ronzini. I'm from the technical direction of SNAM. Now I will take the point of the repurposing. As has mentioned Francesco before, we have 15 kilometers of pipeline that we will reuse from natural gas transport to carbon dioxide transport. This is a pipeline of 24-inch, practically, as I mentioned, 15 kilometers. And this transport will be done in gaseous phase. This is important to mention. All the network, the onshore network between the emitters to the storage site will be in gaseous phase for Ravenna CCS project. So we started a process of certification for the repurposing. Basically, this process involved two phases. One is the approval in principle certification, basically the document collection to perform gap analysis regarding to the composition, the flow assurance, effect of the low temperature, the potential risk of internal corrosion. We did a gap analysis with the standard that were issued before 2025, because this is the date of the certification is 2024. That were the ISO 27913 and the recommended practices from the DMBU. With all this information, we have performed risk assessment, and we got the certification clearly with a technical report, and we define a roadmap for the second phase of the certification, that is the one named technology qualification. What involved a technology qualification? Basically, the topics that were exposed previously in this meeting. This topic of the composition, the impact of the corrosion, fracture propagation studies. So this involved the technology qualification. The current status of this phase, basically, we have solved all the issues. We are finishing the lab testing with our college of ENI that we will enter in more detail later on. And the only topic that is missing to finalize the main details is the final result of the lab testing. With that, we will be able to get the complete certification to reuse this natural gas pipeline. We have another case that we already operated in carbon dioxide with carbon dioxide transport for Ravenna CCS project. That is one pipeline that is connecting the compression station that we will enter in more detail later regarding to the carbon dioxide experimental project. We connected a compression station to platform. And we operated for 1 year this pipeline, and we got the certification, the complete certification. This included this pipeline had a particularity that was operating in a gas phase, but at higher pressure than the typical. It was operating up to 60 bar. This was with control of the temperature. We needed a control of the temperature to keep high values of temperature in order to avoid the liquid phase in the pipeline. We did all this complete process, but this was, as I mentioned before, this was for one experimental project that had the duration of 1 year. For the next slide, we wanted to mention some operational points, and in this case, it's a very nice opportunity to mention the national technical rule that was issued last year in Italy. In October 2025, the government approved and issued the technical rule for the transport of the carbon dioxide. And from the operational point of view, that is a topic that we wanted to mention the main principles. Some you can see them here, that for sure the operator need to do the physical balance, to define the emergency process, the emergency intervention, the maintenance, the coordination with other operators. These are all the points that we already have in one typical natural gas network. But we have one point very particular and very interesting that is for this meeting, is that this technical rule give the right hand, the responsibility to the transport operator to the control and acceptance of the flow entering into the network. This is important to mention, that is the control is not meaning that need to do the measurement enter into the network. So to explain that, we have included a scheme here below. Basically, as you know, the value chain, there is a carbon capture, the compression and the treatment, and after that the meter has a responsibility to measure the composition, to measure the pressure, to measure temperature, and this I will mention that regarding to the composition, there will be two types of measurement. One that will be in continuous, that are the critical components, mainly the big five that we all know, and other component that will be measured with a certain frequency. Why is important that this measurement should be done by the meter? Is because they need to manage the out of specification. They have the possibility in the capture plant area to manage the potential out of specification, and for sure should be avoided the entrance to the transport network. Anyway, the important point is that the transport has another responsibility. The transport network and the operator has another responsibility that is collect all the data regarding to the measurement. So with this data, the transport operator has the right to avoid the entrance of the flow. So in the case that the meter could let's say, inject to the network one flow out of a specification, the transport operator will see the values in continuous, the ones that are critical, and will have the right to block the entrance to the network. I will take a couple of seconds in addition because there were some questions before. The technical rule has specified two types of pipeline, one that are for the connection from the meter and the pipeline that are the main pipes that are going to the storage site. This connection to the meter has some particularities. One is that requires low volume, because in the case, as was mentioned before, enter some impurities. Clearly, it's very difficult to block the entrance immediately. Could happen some minutes that could enter with some impurities. But this technical rule, what is specified? Specifies some restriction regarding some prescription regarding to the inspection. So it's more restrictive than the other pipelines for the inspection. And in addition, reduce the volume of this pipeline. So it should have lower diameters, and the distance between the block valves should be lower than the typical ones. So in this case, the technical rule requires only 6 kilometers. Why this? Because in the hypothetical case that could be a leakage due to corrosion, it's very easy to block the pipe section, and it's a very low volume that could be exposed to the atmosphere. So these are to explain some question that was before, what happened if something arrive to the corrosion. There are some measurement, some mitigation measurement in the Italian technical rule to treat this problem. After the transport, we connect to the storage site. There is another point of measurement that is for the composition, pressure, temperature, in order to be able to control all the value chain, to all the variation regarding to the composition, blending, and clearly the mass flow for included for the declaration too. So I let the towel to my colleagues of ENI in order to continue the.
Okay. Hello to everyone. I'm Maria Giovanna Bagnale and I work in CCS department of ENI. I will introduce you to the first phase of Ravenna CCS project that has been already mentioned by my colleague Francesco at the beginning of this presentation. This first phase has been started up in August 2024. It has been operational for 1 year. It is a small-scale industrial phase that includes CO2 capture from any Casal Borsetti gas plant. The CO2 has been captured from the flue gases emitted from turbo compressors that have a very low concentration of CO2, between 2 and 3%. So this means a very challenging CO2 capture process that has been performed through a highly selective amine absorption process. However, despite this very low concentration, good performances in terms of carbon capture efficiency have been obtained. We had values above 92%. And also in terms of CO2 purity, we had high percentage, higher than 99.5%. Other things we can mention is that in this case, we are able to recover 100% of thermal energy from hot flue gases, and also to have low water consumption because we implemented air cooling. After the capture, the CO2 goes to the compression station and then a conditioning section. So in this slide, I will introduce you about the purification sections we had within Ravenna CCS phase 1. Specifically, we had, first of all, a flue gas pretreatment after the heat recovery steam generator that allowed us to recover heat from the hot flue gases. And through this, we were able to produce steam to be reused in the CO2 capture section for regeneration. So the first part for purification is this flue gas pretreatment that includes the removal of nitrogen oxide. This pretreatment has been necessary both to have a low concentration of nitrogen oxide at the entrance of CO2 capture and also to respect the environmental emission limit for nitrogen oxide emissions from the flue gases. And also this allows to be within the CO2 specification needed for CO2 transport and storage. This was more a consequence of the flue gas that pretreatment that was needed before the CO2 capture. However, there was also a necessity to implement another step for CO2 purification and conditioning that has been placed after CO2 compression. This includes the removal of oxygen. In this case, we implemented a package provided by BASF, including oxidation of hydrogen for the oxygen removal, so catalytic oxidation, and followed by dehydration through a solid adsorption on activated alumina. After the CO2 conditioning, then the CO2 is sent to CO2 transport and storage operations. Last slide I will show you includes the performance we have achieved in terms of purity and in terms of impurities concentration within the CO2 sent to transport and storage network. We can see the values in the table on the right. As I already mentioned, the purity was higher than 99.5%, and all the impurities were below the specification limit. In particular, some critical impurities are as H2S, nitrogen and sulfur oxides were below detectability thresholds, so they were very low and below 2-3 ppm. An important aspect to be evaluated in this project was about the presence of water in CO2. This is because in this case we had CO2 transport in gas phase at about 40-50 bar. And it was very important to avoid condensation and multi-phase transport, multi-phase flow. This is why we had monitored in continuous the water content, but as I already mentioned, there was a dehydration treatment, and also for water we had always been below the specification limit that is 50 ppm. However, we also adopt a sampling campaign to monitor all the impurities and also to specifically verify the CO2 phase behavior and to specifically verify that there were not CO2 condensation, water condensations phenomena that were could potentially bring to water dropout and potentially also to acid species, the dropout of acid species. This was done through the application of a method developed in the Research and Development Department of ENI, based on differential scanning calorimeters, and we have seen basically that with these contents of water, we didn't have any condensation phenomena. This is also confirmed by other UT measurements that have been done on pipelines and that confirm that there were not metal losses. Last thing to be mentioned that this phase was in gas phase, while the second phase will be at higher pressure and in dense phase. So this is why we expect a more stringent CO2 specification for the next industrial phase of Ravenna CCS. This was all about the Ravenna CCS phase 1. Now I leave the floor about my colleague Stefano Franci, expert in corrosion, material and corrosion, that will introduce you to the corrosion tests we have performed.
Yeah, good afternoon. I'm Stefano Franci, materials and corrosion principal engineer, and to support the ENI CCS projects, we have been performing some internal testing campaign. And as already mentioned, the species which are the 5 bad boys, and we look at during our testing campaign are the 5 highlighted in the right-hand side. so water, H2S, SO2, NO2, and oxygen. And yeah, we perform some tests in order to detect any acid formation and eventually dropping out and corrosion issue. If we can move on, yeah. So the initial setup for the testing, it's an autoclave. You can see in the right-hand side with some coupons hung on the top, someone on the bottom. That means, I mean, the materials were carbon steel, standard piping and pipeline carbon steel, carbon manganese material, API and STM materials. And we added also some 316 with a crevice feature because we wanted to simulate any issue for the valve trims which are supposed to be in 316. And so we wanted to test also some CRA, namely 316. The scope of the target of those tests were to verify, as Gerardo said, we wanted to base our composition on facts. So we wanted to verify the impact of the reactions among the pipe bed boys. We wanted to highlight the role of water, also reducing to very low water, because we succeed with very low water in Ravenna phase 1, so we can achieve easily low content of water. And then we wanted to replicate every condition along the pipeline, so top of the line, bottom of the line corrosion. And lately, I mean, we want also to investigate the effect of costs, which is an issue for some emitters and specifically for cement factories. And so we wanted to test also the reaction with the presence of costs, which is, you know, from a literature and from our experience, we don't expect to react and to convert to H2S at CCS conditions, but we wanted to test in this kind of autoclave. This to back up the studies and all this internal testing campaign, we wanted to move forward to answer some other questions, such as the ones raised by Arun, because we cannot shut in, or we don't want to shut in or shut down the plant every time we have a spike. So we want to investigate the damage, a spike, in short duration, how much will be the damage which can be caused by the out of spec or the limits of the impurities. So what we are planning to do is a full-scale corrosion test. Is sketch in a pipe, around 20-inch pipe, fed with gas, with all the impurities. The pipe will be equipped with all the sensors, corrosion coupons, ear probes, and external non-intrusive probes. And those are aimed because we want to test also these devices because we are going to implement those in our plants. So we want to see if they can detect any corrosion or everything going on. So this is going to be a full scale, and the duration is pretty long, from 6 to 8 months, and we are going to change exceed the limits, and so with all the variables, water, SO2, NO2, and so on, and see whether the monitoring system is suitable. And at the end of the duration of the 6 months, we want to open the the autoclave, the pipe, and check inside the damage which was caused by any acid dropping out. And along with this full-scale test, which is able to assess the out-of-spec spikes and the corrosion caused by those spikes, we also want to test the solid deposition, because as an operator, we are concerned about the reservoir clogging the pores, and then we can reduce the injectivity of the in the reservoir, and therefore we are going to test and so all the operating conditions which can lead to salt formation, carbonates, carbamates, and so on, and then to see, if this can cause some problems to our reservoirs. So those are the way forward, because for us, the corrosion rate and the solid deposition is still a gray area, not explored by all the JIPs and all this literature reports. So we want to have this kind of additional info for our project. I guess, and that's it, I guess. So thanks for the attention.
Thank you all for this insightful presentation. I'm not sure whether we have time for the additional Q&A session, but just to let you know that we will keep the space on Miro open for a few more hours. So if there are additional questions, please add them also on Miro along on your name. So we will try to answer to all. And for now, I introduce the last session on applied engineering insights, reducing uncertainty, and I welcome the fellow colleagues of the ENCASE project from IFE, Rainer van Noort and Björn Helge Morland. Please, if you hear, just open your mic and start sharing.
Yes,
The
hello,
floor
everybody.
is yours.
Good afternoon. Can my slides be seen? My slides can be seen. Excellent. So my name is Rainer van Noort, and I'm doing this presentation on behalf of my co-authors Björn Helge Moerland and Victoria Jarushina. We've been asked to tell you a little bit about the experimental research that IFE has been doing into the impact of impurities on material integrity in both transport and storage systems. There's already been a lot of talk about the transport system, so I think I'll go through these first slides a bit faster and focus a bit more on the storage part, because there's been some questions about that. Also, I'm a geologist myself. Björn Helge Moerland is the corrosion specialist, and as he's not present at this moment, I can only just repeat what he told me, really. So I can skip this slide. These are the key reactions that take place with different impurities that can lead to acid formation and corrosion. I've seen them on different slides already, so we'll skip them. And basically, at our corrosion department, my colleagues have been working on different scenarios during transport and understanding how corrosion can occur. So I have 4 slides here. The first slide here, we see what can happen already during the commissioning. So when a new pipeline is built, you test it with water and glycol and inhibitors to see whether it's pressure tight, and that's being tested here in this setup where an electrode system is used to monitor changes in corrosion on the steel coupon in the center of the cell. Typically, even though you have water, you have oxygen, it's possible that the corrosion rates can be high, but overall it's going to be very low corrosion because of the short duration, as long as you make sure to properly flush out everything afterwards using air, nitrogen, or just the CO2. Then next, kind of an example of what can happen during transport when everything is according to spec. So and kind of showing the research going behind the development of these specs. So at the top, we see a cell with CO2, SO2, and water. And at the bottom, we see a cell with similar contents in CO2 and water, but with NO2. And the difference between the two is very important. So research has shown here that in the presence of NO2, water can precipitate even when it's only at about 10 to 50% of saturation, whereas with SO2 that does not happen. So this shows the importance of testing not just individual impurities, but combinations of impurities, and then taking one impurity and changing the concentration to find the critical ranges. So at the top, even at about 90% water content, it's going to stay in solution in the CO2 phase. At the bottom, you see this surface-specific corrosion, so this film of acid corrosion taking place on these steel coupons with only about 10 to 50% of water. Next, showing an example of minor upsets, minor deviations. It was already mentioned in discussion. What happens if something goes wrong at one of these capture installations and dirty CO2 is sent into the pipeline and you quickly shut it down? This is some research on that. On the whole, the total quantity of corrosion is going to be limited by the quantity of acid-forming impurities that are introduced, but you do have the chance that because these reactions are hygroscopic, they will localize. So even if the overall corrosion compared to your pipeline system is going to be very limited, it can be localized, and repeated localization, of course, will mess things up. So it is something to keep in mind. And finally, some research in like worst case scenarios. What if you get really icky stuff going into your pipeline? And as you can see, the colleagues at Corrosion don't even want to use their pressurized equipment for this sort of research. So it's just being done in glass beakers with a low CO2 pressure. And you can see that can have some very strong effects here. And again, it's mostly going to be limited by the amount of acid relative to the surface area of the steel of the system. So moving on then from transport to storage. And this kind of shows how this research goes into specifications, and you can see this development of specifications with initial specs in the early 2000s being based mostly on keeping people safe, and later specs as corrosion research became available, changing towards keeping the pipelines intact and preventing any corrosion. And I think one important point that Björn wants me to reiterate here is that if you make a specification specific for one system, as other people also mentioned, you can be much more lenient with certain impurities if you know that others are not going to be there. So that's kind of shows the importance of understanding this as a system and understanding how different impurities affect one another and how these reactions that I showed earlier are the key thing to keep in mind, and not just individual impurities. So yeah, then storage. So my key point here is that ensuring well seal integrity may be the key challenge when you look at storage. Here in Europe, we're mostly looking at storing in siliciclastic reservoirs. So these typically consist of sandstone, quartz, and other silicate minerals that have already gone through a whole erosion process, a bunch of transport, etc., and stayed intact over thousands, millions of years. So typically these are fairly stable minerals. If we look at some of the projects, for example, in the Arabian Peninsula, where they're looking at storing into carbonate reservoirs, the story may be a bit more different, as carbonates can be, of course, very reactive. Also, the cap rocks over most reservoirs are shale, clay-rich rocks, relatively stable, though in some cases there may also be anhydrite or other evaporites that could be more reactive. So overall, I would say more research is required, but the impact may be limited. I have another slide coming up. However, when you want to inject CO2, you need to drill your hole, you need to put your steel pipes in place, and you need to put a seal between the pipe and the cap rock to ensure everything just stays there and doesn't come up again. And these man-made components that we're introducing into the storage system, these are relatively reactive and could be a key vulnerability in ensuring storage integrity. So I just introduced this slide after the question. When you inject CO2, you can see on the image on the left here that we're going to form a dry plume, which the people unfortunately chose to make blue in this image. Displacing the CO2, the CO2 is dry, is being injected, and it's displacing the pore water in a saline aquifer, and you get this dry CO2 zone around the injection well, and then a transition with gradually more water until you're in the water saturated reservoir. When we have the impurities in the CO2, they can be kind of identified as either water partitioning or CO2 partitioning, and that will have a very big impact on where they go in the system. So when the CO2 spreads through the reservoir, the CO2 partitioning impurities will travel with it, whilst the water partitioning impurities will partition into any water phases. So when you have some water trapped in pores or on surfaces, that's where these impurities will go. And as you can see in my list on the right, that's that's especially the SOx, the NOx. So the acid forming impurities will typically stay close to the wellbore, close to the injection site, and not spread far into the reservoir. But that also means that their impact will be concentrated there. Regarding that impact, we can kind of identify 2 or 3 different main chemical impacts. On the one hand, we have impurities that increase dissolution. So as I said, acid forming, etc. On the other hand, we'll have impurities that increase precipitation. Taking the example of a carbonate reservoir, if you then introduce SOx, if that forms sulfuric acid, you'll then react that to form gypsum or anhydride, which may have a larger volume than the calcite it's replacing, etc. And these, even though the total volumes of impurities are going to be very limited, if you have these reactions taking place in key parts of your pore network, they could have a big impact. So especially easier to explain with the precipitation. If that clogs narrow pore throats, it will mess up your injectivity, even if the impact on capacity is going to be very limited. So yeah, that's just a quick extra bit about what it does in the reservoir. The caprock, similar, but caprock overall is very tight, so these reactions are going to be limited in how far they can penetrate into the caprock, as the CO2 doesn't penetrate deep. But as I said, the sealants, the cement sealants around the well may be a much more vulnerable spot, because cement sealants are typically based on Portland cement, which has a very high reactivity with CO2, forming calcite. And if you have a continued exposure to CO2 saturated brine, this calcite may subsequently dissolve, and then you get proper degradation. So we see here some research from the Cementegrity project. At the top, there's an unexposed, fairly standard cement. At the bottom is the same cement after exposure to CO2 saturated water for half a year. Yes, I think it was half a year. 16 weeks, actually. So much less than half a year. Yes. And then we also exposed the same sample to wet supercritical CO2. So one was placed underwater in the autoclave, one was placed above water, and there you see it looks very different. We don't see this degraded outer zone where calcite has been dissolved, and instead we see a more gradual change. So carbonation leads to more solid formation and actually can improve the quality of your seal, but leaching will mess it up. But then what's the impact of impurities? This has not been so studied so widely, but here we see the same sealant again, exposed to CO2 with 1.6 mol% H2S, either underwater or above water, and exposed to CO2 in the presence of concentrated sulfuric acid. So in the same autoclave, we had the samples, we had a CO2 phase, and we had concentrated sulfuric acid to create a realistic H2SO4 SOx concentration with a big quantity, so that the batch process could keep going. And we see some very clear differences in how these samples look, especially with the H2S, of course, where oxidation states are going to be very different. If we look at the same samples in the CET, we kind of see the same patterns. We see that the ones exposed to CO2 saturated water have a clear leaching, a decrease in density that we also see as different colors there. Whereas the ones exposed directly to the CO2 phase are more gradually changed with some densification at the edge. But just these optical and CT images and SCM that we did doesn't give the full picture. We need to look also at XRD analysis to understand what's happening in these reacted zones. So looking first to the samples exposed to clean CO2, we see how some of the typical cement minerals, tolumarite, catoite, disappear and are replaced by a carbonate precipitation that's initially vaterite and then subsequently replaced by calcite and aragonite. So we see metastable vaterite precipitating first and being replaced or even removed if there's CO2 saturated water. And this is a paper that we wrote with support from ENCASE. So that's currently published, awaiting review on Open Research Europe. If you look at the sample exposed with H2S, the interesting thing here is that the biggest difference, well, there's two big differences. One is that the calcite or the carbonate content is reduced even more. The other interesting difference is that we see the appearance of a few percent of gypsum in this outer reacted rim. And, you know, we injected H2S, not SO4. So this clearly indicates that the H2S, the sulfur there, has been reacting with minerals in the cement, likely the iron minerals, reducing Fe3+ to form SO4 and then precipitate as gypsum. So that's a very interesting observation, showing that these systems are still more complex than you think, and showing the importance of interaction between minerals and impurities in these systems. So this XOD study that we did gives a clearer picture of the mineralogical changes and emphasizes the impact of impurities and that we need more study to properly understand this, as it's more complex than we would have expected initially. So yeah, clearly further study is needed. We also need to look at the impact of these impurities at the cement-steel interface, which may be an even greater zone of weakness or risk, I should say, for integrity than the steel itself. And that's something that we should be doing more work on. How then do we go from having this small-scale experiments to understanding what happens over thousands of years? Of course, that requires modeling. So that's where Victoria comes in, my collaborator and supervisor. So here we see some carbonation depth from the experiments. We see that the diffusion-controlled progression is dependent on the square root of time. And then a simple reactive flow model combining chemical conversion, advection, and diffusion. We can see that for the model can show quite nicely that when you have a fast reaction, you can still get a sharp reaction front, even if you have a diffusion-dominated system. So that's some in-prep work, as well as a presentation we did in Trondheim last year. So, and this modeling framework that we're building here for cement will easily be adapted as well for other parts of the storage system. That kind of all I had to say for today. So thank you for the time. And if you have any questions, I guess I'll see them somewhere.
Thank you very much. Let's see if there are additional questions. This is the moment. Okay.
Hello there. Can you hear me?
Yes.
Yeah, I'd just like to thank you, Rainier, for the presentation. I'd just like to make one comment, which I think hasn't quite been covered maybe today, is that there's a great deal of interest in reusing oil and gas infrastructure for CO2 storage purposes. And in the case of CO2 injection into depleted gas fields where the pressure can be low, you can get kind of Joule-Thomson cooling near the wellbore region. And the introduction of additional impurities like nitrogen can affect the Joule-Thomson cooling, and it could potentially result in lower temperatures compared to pure CO2. And this is an area which is kind of currently underexplored in terms of the thermodynamic modeling. And it does present risks in the case of hydrate formation at lower temperatures. I'd just like to make that point. Thank you.
Yes, indeed. I focused on chemical impacts, as that's what I've been working on. But in the Cement Integrity project, we also looked at some of these thermal effects. And again, the interfaces are probably going to be the key part to think about the steel cement interface and cement epoch interface.
So, I think there are not any other questions, at least from the chat.
If I may take 5 more seconds, I should reiterate that overall these reaction fronts are progressing quite slowly. It's millimeters per year kind of thing, or less. It's not something that we should be very alarmed about. I think the challenges with corrosion in the steel pipeline are much more significant overall. But it is important to understand these risks.
Thank you, Rainer. So I think this session is coming to an end. I would like to take a moment to thank all of the people that joined us today, participants, speakers, and the cluster of projects for these meaningful exchanges of knowledge and insights and related presentation. We couldn't have done it without you. So really, thank you. And before closing, a few items, and I will leave the floor to Massimo.
Yeah, before everyone leaves, we would like to thank you all again for joining this webinar. And about the slide and presentation, as you asked in the chat, you will receive via email in the next few days a link related to the online page containing all the slides, so you can download all the presentation in PDF for future consultation. In the same email, we will also try to give an answer to the additional question we received in Miro board. And basically this page will also contain the workshop recording. As you know, we are also live on YouTube. The video will be available on our official page on YouTube. So if you want, you can share it on social media, newsletter, and so on. And we also remain available if you have any feedback about this webinar, or if you have any question or curiosity or anything. If you want to keep in touch with us, follow the NK project social media. You can find the links in the chat. Thank you again for joining.
Thank you, Massimo. And once again, thank you all for joining us today. That is it. Have a great afternoon, a great weekend ahead, and see you the next time.
Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.
Thank you, everyone. Thanks to everyone.
Goodbye.